So, hello students, how are you? Welcome to my channel Physics with Rams. So today we are going to discuss about a kinetic theory of gases, and this is my second video based on this kinetic theory of gases. As we had seen kinetic theory of gases in the first video, and we had represented the pressure acting in the case of gases, and we had represented the expression for pressure in the first video. So before going to watch this video, please watch my first video so that you can get some clarity regarding this video. And remember that while studying physics, please try to analyze the subject. By analyzing itself, you can understand the physics in a easy way. And as I know that your target is JEE mains as well as NEET, try to revise the syllabus and try to revise the concepts in a way such that you can understand the concepts very easily. You can understand the concepts very easily when you try to understand the concepts by analyzing. So please try to analyze the subject while reading. After that, in this video we are going to discuss about degrees of freedom. Degrees of freedom, as well as a law of equipartition of energy. Law of equipartition of energy. So now here in this video now we are going to discuss about the degrees of freedom. So observe that as we consider this degrees of freedom, so here we are going to represent that the minimum number of ways or which the motion of the body can be described completely is known as degrees of freedom. So here we are representing that the minimum number of ways or the motion of a body that can be described completely is called degrees of freedom. So here when we consider a body on a horizontal surface, whereas the body is of a mass m, and if we push the body in this direction by applying a force F, then here we can represent that the body can move along this direction. Suppose if we apply the force on this body along this direction, then we can represent that the body can move along this direction, means it is moving along the horizontal direction. Based on that, here we can represent that the degree of freedom for this body is 1. Means since it can move along any one dimension, we can represent the degree of freedom is 1. Suppose if we consider an plane based on x and y axis, and here if the body has been projected up by an angle of theta such that the body travels like this. Observe that the body is traveling along a x and y plane. It's traveling along a x and y plane. So since the body is moving along the x axis as well as along the y axis, here we can represent that the degrees of freedom is being represented as 2. Why? Because it can move along a two-dimensional way. Whereas similarly, if we consider a body which is rolling on the surface, observe that here the center of part of the body, it can move in a straight line, which is represented as a translatory motion, as well as the body rotates, which is represented as a rotational motion. Whereas combination of this rotational motion and translatory motion is being represented as a rolling motion. Observe that this body is moving. If we consider it as a heavy body, this body is having a rotational as well as a translational. Based on that, here we can represent that the degrees of freedom for this body is being represented as 2. So similarly, if we consider this body as a molecule, if we consider it as a molecule, then here we can represent that this body possesses 3 degrees of freedom. Means here what happens, the body can move in a translatory way as well as a rotational way, as well as it can move along the 2-dimensional axis. Why? Because when we consider a molecule, it can move along the y-axis as well as it can rotate. That's why we can represent that a molecule possesses 3 degrees of freedom. Take a screenshot. We will continue. As we had seen degrees of freedom for different bodies, now we are going to discuss the degrees of freedom for gas molecules. So here when we consider a monoatomic gas, let us consider a monoatomic gas. So after that monoatomic gas possesses monoatomic gas consists of a single gas molecule, and based on the origin, the gas molecule can move along x-axis, along y-axis, as well as along the z-axis. So observe that this molecule can move along any one of the axes. Here we can represent that the monoatomic gas is having 3 degrees of freedom. It's having 3 degrees of freedom. Whereas when we consider a diatomic gas, observe that the diatomic gas is nothing but it's a combination of 2 atoms, nothing but just like O2, H2. Like this, we can consider the molecules which are the combination of 2 atoms. So here, since the atom is being considered based on the molecule is being considered based on the 2 atoms, hydrogen and hydrogen, which are being separated by a distance. Observe that these gas molecules can move in the upward direction as well as downward direction, as well as they can move along this direction. Here we can represent that this diatomic gas molecule is having 5 degrees of freedom. 5 degrees of freedom. Why? Because here we have up and down for this molecule, as well as we have up and down for this molecule, as well as it's having a rotational motion. Means it can move in a translatory way, as well as it can move in a rotational way. So based on that, here we can represent that this gas molecule is having a 5 degrees of freedom, 3 degrees of translational and 2 degrees of rotational. So complete is 5 degrees of freedom. Whereas here when we consider a monoatomic gas, here what happens is it has only 3 degrees of translatory motion. In the same way, when we consider a triatomic gas, based on the nature of the triatomic gas, we can represent the degrees of freedom. Suppose if we consider a triatomic gas which is in the form of a triangle. In the form of a triangle, just like a CO2, H2O. All these molecules are triatomic molecules. Observe that when we consider these triatomic molecules here, we can observe that they have three translational degrees of freedom. Why? Because it can move along x-axis, y-axis and z-axis, as well as they can rotate along the x-axis, they can rotate along the y-axis, as well as they can rotate along the z-axis. They can rotate along the z-axis. So based on that, here we are representing that a triatomic molecule is having a 3 translational as well as a 3 rotational. Based on that, here we can represent that a triatomic gas is having a 6 degrees of freedom. Similarly, when we consider a triatomic gas which is in a linear form, which is in a linear form, then here the number of degrees of freedom can be represented as a 7 degrees of freedom is being considered when we consider a triatomic gas which is in the form of a linear path. Take a screenshot, we will continue. Now we are going to discuss about law of equipartition of energy. According to law of equipartition of energy, when we supply a energy to a gas molecule, then the energy is being splitted up by the molecule in translational, rotational and vibrational. So based on that, here we can represent that the total energy is given as energy due to translation and energy due to rotation plus energy due to vibration. Whereas let us consider a diatomic molecule. It is being moving in the forward direction with 5 degrees of freedom when we consider a diatomic molecule. So now here, based on that, we can represent that since it is a diatomic molecule, it can move about a fixed axis. It can rotate about a fixed axis, whereas the number of rotations can be represented as 2. Already we had represented it as 3 degrees of freedom in the case of translational and 2 degrees of freedom in the case of rotational. So complete degrees of freedom is 5. So the total energy is being split up in terms of translational as well as rotation. Whereas the kinetic energy for the gas molecule is being represented as half mvx square along the x-axis, and the energy along the y-axis is being represented as half mvy square, and the energy along z-axis is being represented as half mvz square. Similarly, due to the rotation, the energy is being represented as half I omega I1 omega 1 square plus half I2 omega 2 square. This represents the expression for energy, kinetic energy in terms of moment of inertia and angular velocity. Since they are rotating about a fixed axis. So based on that, we can represent the expression for law of equipartition energy based on the degrees of freedom. Similarly, when we consider a molecule like a carbon monoxide, when we consider a molecule of a carbon monoxide, observe that at moderate temperature, the atoms oscillate along the interatomic axis like a one-dimensional oscillator. Then the vibrational energy when we consider CO molecule, here we had represented that it possesses a vibrational energy. Then the total energy is being given as E equals to E suffix T plus E suffix V plus E suffix R. This represents the rotational as well as the translational and vibrational energies. As we consider this condition, here we are going to represent that the vibrational energy is being given as 1 by 2 m into dy by dt whole square, which represents the kinetic energy due to translational plus half ky square, where k is the constant force constant of the oscillator in the case of vibrational terms. Take a screenshot. We will continue. Now we are going to discuss about heat capacity in terms of degrees of freedom. So now here the degrees of freedom is being represented based on the energy. As we had seen that the kinetic energy of the gases based on the internal energy can be represented as F by 2 nR into delta T, where delta T is the change in temperature, R is the constant, and N is nothing but it can be represented as N by N suffix A. This represents the value of small n, where F represents the degrees of freedom. So here, as we consider the specific heat at constant volume, it can be represented as a change in the heat at constant volume by N into change in the temperature. So now based on that, here we can represent that delta Q at a constant volume is equals to N into C suffix V into delta T. As we consider that the amount of heat transferred at the constant volume is completely converted into internal energy. It is utilized to increase the internal energy. Based on that, here we can represent that delta equals to N into C suffix V into delta T. Whereas at constant pressure, the amount of heat transferred is utilized to increase the internal energy as well as to do external work. So the relation between specific heat at constant pressure and constant volume is being represented as C suffix P equals C suffix V plus R. So here based on that, as we consider this equation, specific heat at a constant volume can be represented as delta U by N into delta T. As we substitute the value, observe that F by 2 into N R delta T by N into delta T. Delta T gets cancelled and N gets cancelled. So here we get 1 by 2 into F R. So when we substitute the value in this equation, here we can represent it as F by 2 into R plus R. Nothing but when we take R as common, here we can represent it as F by 2 plus 1 into R represents the specific heat at a constant pressure. So based on that, the ratio of the specific heats can be represented as gamma equals to C suffix P by C suffix V equals to F by 2 plus 1 into R by F by 2 into R. Observe that R and R gets cancelled. So here we get a F by 2 plus 1 by F by 2. On simplifying, here we get a 1 plus 2 by F is the ratio of the specific heats of the gases. Take a screenshot. We will continue. As we had represented that gamma equals 1 plus 2 by F 1 plus 2 by F for the degrees of freedom. Now we are going to consider a monoatomic gas. So as you consider a monoatomic gas, here observe that the degrees of freedom for a monoatomic gas is 3 degrees of freedom. So based on this number of degrees of freedom, here the ratio is being given as gamma equals to 1 plus 2 by 3. As we consider this, 3 plus 2 is 5 by 3. So here based on that, the value of gamma can be represented as 1.66. So when we consider a diatomic gas, we had represented that it possesses 5 degrees of freedom. Then the value of gamma can be represented as 1 plus 2 by 5. Nothing but 2 by 5 is 7 by 5. So here we get 1.4. When we consider a triatomic gas which has 6 degrees of freedom, then here it can be represented as gamma equals 1 plus 2 by 6, nothing but 1 plus 1 by 3. So here we get 4 by 3. 4 by 3 is nothing but 1.33. So here we can represent the degrees of freedom for different gases based on the value of gamma, where we know that gamma is nothing but it's a ratio of specific heats. So when we consider a gas molecule with F degrees of freedom, here the kinetic energy per mole is being represented as F by 2 RT. Similarly, it's given in terms of moles, whereas the kinetic energy per molecule can be represented as F by 2 K into T, where K is a Boltzmann constant. It's a Boltzmann constant. Based on that, here when we consider a monoatomic gas, it can be represented as kinetic energy is equal to 3 by 2 K into T, whereas when we consider a dia, the kinetic energy is being represented as 5 by 2 kT, as well as when we consider tri, the kinetic energy can be represented as 6 by 2 kT, nothing but it's given as 3 kT. This represents the kinetic energy per molecule. So now when we consider in terms of moles, the mono is being given as kinetic energy equals to 3 by 2 RT, whereas in the case of dia, the kinetic energy is being represented as 5 by 2 RT, and in the case of tri, the kinetic energy is being represented as 6 by 2 RT, nothing but 3 RT. 3 RT. In this way, we can represent the kinetic energy as well as the value of gamma for mono, dia and triatomic gases. Take a screenshot, we will continue. Let's solve a problem based on this concept. Observe that a cylinder of a fixed capacity 44.8 liters contains helium gas. It contains helium gas at a standard temperature and pressure. What is the amount of heat needed to rise the temperature of the gas by 15 degrees Celsius? So now here we have to represent the amount of temperature needed to rise the by 15 degrees Celsius, heat needed. So the value of R has been given as 8.315 mole per Kelvin. So this is the value given for R. So here, since the volume has been given as 4.8 liters, so we know that the volume at STP has been given as 22.4 liters. We know that at STP the volume occupied by the gas molecule is being represented as 22.4 liters. So it represents 1 mole. So based on that, here we can represent 44.8 liters. 44.8 liters represents 2 moles of gas. So now based on that, here the expression for a specific heat at a constant volume can be represented as a 3 by 2 R. Why? Because it's a helium gas. Whereas the specific heat at constant pressure can be represented as a 5 by 2 R. Then here the heat required can be given as a dq equals to n into c suffix v into dt. Here the change in the temperature is being represented as a 15 degree Celsius. Then the expression can be represented 2 into the value of c suffix v is 3.2 r, nothing but 3 by 2 is nothing but 1.5 into the value of r is 8.315, whereas approximately it can be considered as 8.31 into 15. So here it can be represented as 45 into 8.315, which is equals to 374 joules, which is an approximate value. Take a screenshot. Please share this video to your friends, like this video, give a like to this video, and subscribe my channel so that you can receive notifications regarding my channel, as well as you can watch my previous videos so that you can clear your concepts regarding physics, as there are lot of videos regarding first year in my channel. I'm going to start second year from the next videos. Please stay tuned to my channel. Thank you.